Let's start. It's a great pleasure for me to introduce you Jozsef Solymosi from the University of British Columbia, who will talk about the clique number of polygraphs. Thank you.
Thank you very much, and thanks for this opportunity. I'm glad to give this webinar, or I don't know what is the official name of that. And I will talk about polygraphs, and of course, as usual, I have more questions than answers. Some of the questions might be hopelessly difficult, but others are really, I think, attackable, but we will see. So part of this work is joint work with my excellent graduate students, Daniadi Benedetto and Ethan White. Right, so polygraphs. Oops. I'm not sure. I'm not doing. Okay, let's use this. So polygraphs are usually defined over finite fields for primes which are 4k plus 1 forms, so p congruent 1 mod 4. And then the polygraph where the vertex set is fp, so we have p vertices. And then two vertices are connected by an edge. If x minus y is a quadratic residue, that means that over this field it's a square. It's a square of a number. And because it's 4k plus 1, the form, it's symmetric. So if x minus y is a quadratic residue, then y minus x is also a quadratic residue. And I'm going to use this notion, this chi as a character, which is 1 if the number inside is a quadratic residue, minus 1 if it's a non-residue, and 0 if it's 0. Okay, so this is an example for a polygraph for 17 vertices. There are many important things about polygraphs. I won't really have time to talk about the nice features of them. The most important thing is, among the most important things, one is that polygraphs are quasi-random graphs. So they are good models of random graphs, although there's, well, I wish we could really prove the random properties of the graph. Okay, so this is the graph, and one question which one can ask with the graph is that what is the clique number? So as I said, it's a quasi-random graph, but still we don't know really what is the right magnitude of the clique number. The upper bound was improved very recently by Hanson and Petridis, and I will show a different proof for that upper bound. And the lower bound, well, what you see here, it's not really a lower bound on the so for some p's, this is a lower bound. So what it shows is that there are some values, there are some primes when the chromatic number is larger than what you see in a random graph, where it would be just log. So it's more. So that was done by Graham and Ringrose. Under the generalized Riemann hypothesis, you can improve this lower bound just a little. You can remove one log, so it would be log p times log p for some p's. But what is the general bound for this? So there is I didn't find much about this. There is a relatively, now we say, old paper of Cohen, where he gave a bound on the clique number. So as I said before, those lower bound values which you see there are just for very few primes will hold. In general, we don't know what is true. So Cohen proved something, but that's by now is weaker than the bound we know for the general graphs, any graph. And there is this recent development, beautiful result, where it was slightly improved. So Ashwin improved the diagonal Ramsey number. So the improvement here is this, you can divide 2k choose k by this e to the c to the log k squared, which is better than any polynomial. But still, it's about 4 to the k. So the magnitude is still the same as it was ages ago, after the first simple proof by Erdős and Szekeres. And one would expect maybe that for Paley graph we can do better, and indeed we can do better. So I will show you one example here. I don't think this result is sharp. I think that the constant can be improved by more involved calculations, but this is a relatively simple bound. I'm going to show you that for Paley graph, so you see for arbitrary graphs, the best bound is about 4 to the k. If n is larger than 4 to the k, then there is either a k-sized complete or a k-sized empty subgraph, right? And for Paley, at least it's something like 3. But I'm sure that it can be pushed down further. But let's see the proof of this one, how to use this quasi-randomness to gain this improvement. This is the first part of my talk, and after that, as I promised, I will give you the upper bound, which is also an important open question. So both questions are open. Here, the immediate challenge would be to go closer to 2, which somehow I don't know what to think. So let's see this one. Let's see this bound. So we want to use some kind of structure, special structure of Paley graph. So for that, let's see this lemma. It's relatively simple counting I came up with. If you have a very small set, in this case, small means that about base 4 p log, minus even a little more, then this is still a set which is not too large, and it still has many common neighbors. So you see this notion, this I'm using this kind notion. So that means that there are many elements in this finite field where all the differences from this element E to all AIs are quadratic residues. Okay, so the statement is that many means here the most important part. You see, size of A is about log, so focus on the root P term. That's what is important. So you have more than root P such points which are connected in this Paley graph to all of the other vertices. So all AK, A1, A2, AK. Right. And so how to prove something like this? Well, I write a polynomial, a product, which will count the number of such points. So let's see this product. Product chi x minus ai plus 1. Now you remember chi is 1 when it's a quadratic residue, and minus 1 if it's not. So if there is any of them is not a quadratic residue, then this product is 0. And if they are all quadratic residues, then this product is 2 to the k. So this will be our counting function, but let's see how to deal with such thing. There is also the other case when AI is x. So x is one of the AIs, but that's a very small, say, error. We don't have to worry much about it. So this is the strategy now to prove the lemma. We will check how many such elements are there. For every such E, this product will be 2 to the k. Okay. So in order to deal with such a product, you have to break it into parts, and that's what we do here. So we write it as well, you break the big product and you have the terms here. There is one which is 1, and the others are various products. Now, at this point, and of course, you have to use the multiplicativity of this character. So you know that for every fixed I, the interval, the big I, so for every subset of the index set, when you have this I, then that's just a polynomial of degree of the size of this subset. And this, well, chi of this polynomial. And this polynomial has distinct roots. All the roots are distinct. It's important in order to apply whatever we have to apply soon. So this is a nice polynomial. So let's go back. That's our counting function. I just repeat here this product, what we have down there, but we already modified it. We have a different form now. And in order to count it, so this gives 2 to the k whenever x is such an element, e in the previous statement. So I divide it with 2 to the k, and it will count 1. Every time when you have an x, which is a good element, where all the differences to the other elements are quadratic residues, then it will count 1. So this will be a good counting function, and you run through all possible x's over fp. Good. So you work a little, not much. So clearly the first term is p over 2 to the k. You just summed p times 1, and then what you left with is this form where I yes. We didn't really do much here. Here again, the note that this counting is not exact because of 0, but that's just a very minor error, so we don't have to worry about it, right? Right. And our main tool here to bound. So if you remember here, the right-hand side is something we want to do with. So we want to somehow bound this sum where x goes through the whole finite field. But luckily, there are those beautiful results. One of them is, the bounds, very bounds on character sums. This is a relatively simple case. It even has an elementary proof. So if you see this sum, then we know that in this case, remember that those GIs are nice polynomials. It's smaller or equal than the degree of the polynomial minus 1 times root p. Right, so this is the bound. This root p is always there whenever you work with character sums. And now, so please note that our bound now is independent of the polynomial. It only depends on how many roots are there. What is the degree of your polynomial? So you just do this summation. It's a simple binomial sum, and there was in this condition in the theorem that we wanted to prove this for relatively small sets, yes, when k was smaller, much smaller than base 4 log p, and then it's just a simple substitution to get the result. So we have this result, the lemma is proved, and the lemma says that if you have any small set in your Paley graph, a small set of vertices, then there are many other vertices which are all connected to all elements, which are connected to all of the elements of this small set. So here is the strategy now to bound the clique number. We are ready to actually prove what we wanted to prove. So the strategy is, let's find a complete subgraph, a small one. You can do that because it's guaranteed. Maybe at this point, let me also mention that the Paley graph is a self-complementary graph. So if you have, so to find a complete graph is the same as finding an empty graph, because you just multiply every element by a quadratic non-residue, and whatever was quadratic residue is a quadratic non-residue, and whatever was a quadratic non-residue is a quadratic residue now. So let's not worry about finding such a complete graph. So you find a complete subgraph of size a little less than what is guaranteed by Ramsey, but that's fine. This is not our final result, but it's small enough that we have this property that many other vertices are connected to all elements, or with other words, so this is by the lemma what we had up there, is that there are many vertices, this V, V1, V2, Vm, where m is more than root p, such that their common neighborhood, so the intersection of the neighborhoods, contains this complete graph. See, now we can just gain, because the k is almost as large as what we were able to do with regular graphs, and now we still have this root p-sized set where every vertex is connected to every vertex of this small clique. So here now we do a kind of optimization. Either we find a very large empty graph here, just using classical Ramsey, or we have somewhat smaller complete graph, but this will increase the size of the complete graph we started with. So find a clique or a somewhat larger independent subgraph. And now, well, it's just counting. As I said, this is just the kind of classical Rédei formulation for graphs. So if you have, now there's C and L, I will specify them in a minute, but it's just formally, you know, if you have this binary form and this inequality, then you know that M, which is now this big V, the number of vertices, V1, V2, Vm. So there either you find a large, in this case, 1/2 plus C times L, L stands for log, we will see in a minute, or you will find a complete with C times L. This 1/2 here is that, so we want to beat the fourth, the base 4 log, and we want to have a better exponent there. So 1/2 is the improvement above that. So let's see. So here is what I said, that of course this C, you will see it's a result of an optimization, but L is log 2 P, base 2 log P. And if you use those values, then this binomial coefficient will be a little bit below M. And here is, well, it's kind of technical, but it's a simple counting. So you just use approximation for the binomial coefficient. In this range, you use the entropy function. That's a good approximation. And that this right-hand side, so this is still the same binomial coefficient what we had before. You want that on the right-hand side you have this well, base 4 log p. So this is log base 2 root p. So then you see that this happens when this equation, you solve it for the last one, for C, the equation down there, and you solve it where you use I use some computer and you get this number. And with this number, we are actually ready to compete. So you have either this large 1 plus C size, 1 plus C times base 2 log P empty, or the same complete. And if you check what it gives you exponent, for the exponent, it's really, well, it's not exactly this number, but something like this, a little bit smaller than 3.009 to the C. Okay, so that was the lower bound. Now I told you that I will ask many open questions. This is an open question where I think a good approach can improve this exponent. I really don't think that would be a limit of methods. A better use of exponential sums or character sums or a slightly better strategy would give you a better exponent here, I'm pretty sure. So upper bound. Upper bound. For a very long time, the upper bound even for fp was just root p. Root p is easy to see. So if you see the Paley graph, and if you remember that this is self-complementary, so we had this, say you have the largest clique, then you have a same size empty clique, yes, and you can translate your clique, you can shift it with any values from this empty clique, and if you see, all those translates should be disjoint. All those translates should be disjoint, because if there would be an intersection, then with that translation, which gave you this intersection, there the different two elements would be a quadratic non-residue from the clique. So all those entries are disjoint, so that's immediate that square root p is a bound, or to that end square root q if we have a power of p. And indeed, this is sharp for p squared, say, when your field is p squared. But for prime, it was conjectured that the truth is actually somewhere power of log. But even to break root p was very difficult. There's a nice paper of Bahok, Matocci, and Ruzha, where they proved at least square root p minus 1 for many primes. But then there was this Hanson-Petri, this nice method for using the polynomial method, actually using some kind of simplified Stepanov's method to get a bound, which is now the best. And it seems like a natural bound. I will tell you why. It's root p half. So it's a constant improvement. It's a constant multiplier. It's a multiplicative improvement. It's great. So let's see now, how did we arrive to the same bound? And that's why I think that something is happening there. So a small detour. We will talk about directions. So you have, say, fp cross fp, and you consider the points there. Or to be more correct, we have the affine plane. And we are talking about the direction. So any pair of points will define a direction. It might be the infinity or whatever. And so this is the direction. This is how we define the set D. You have points. For every point, you have two coordinates ai, bi, and the directions are defined like this, as usual, as you would do in Euclidean geometry. There is no difference at this point. Right, and so you have all possible values, and you also have the infinity. So when ai equals aj, and this set of directions, for example, is 1 if all of the points are on a line. But if the points are not all on a line, then we expect that the number of directions is much more. In order to handle this problem, there is a beautiful tool. It's a so-called Rédei polynomial, which I will briefly introduce now, which we are using. First, the definition, and that's actually also the title of Rédei's book, Lacunary polynomials. And it means that you have the first term, the leading power, in this case x to the 100, and there is a huge gap to the next exponent, non-zero exponent. So in this case, this is 1. So you have the gap between the highest and the second highest term is huge. And so let's see, what is the Rédei polynomial? You have a point set that will define this polynomial. You have a point set, so ai, bi pairs in the plane. And you have this polynomial hxy equals, for every point, there are n points, x plus ai times y minus bi. Now, this is a very interesting polynomial. This polynomial will really tell you the algebraic property whether a direction is defined or not. So how? You see, if your point set did not define y, a direction, then all the values here in this product, this x plus ai y minus bi are distinct. You won't see it twice, because if you had that ai times y minus bi equals aj times y plus bj, or minus bj, there is a typo, doesn't matter, then you see that y equals bj minus bi, so y is a direction defined by the points. Sorry about this plus here. You see, so let's go back here. The Rédei polynomial is an algebraic tool which will really tell you if a direction is defined by your set or not. If the direction is not defined, that means that if you substitute to y, then you have this product x plus some number which depends on the selected y and ai and bi. For every I, you have distinct numbers. So that means that this polynomial for that y is fully reducible. All the roots are in Fp and all of the roots are distinct. Okay, and there will be a reason to see this polynomial in this way. This is x to the n so we consider the y parts as coefficients. So x to the n plus h1 y times x to the n minus 1, so on, so on, so on. So you see in hy, the degree of that polynomial is 1, and in general in h, j, y, x, n minus j, the degree is j. So that was Rédei's result. He used this polynomial when the number of points was exactly p, as fp, so the prime. And you know, so if y is not a direction, then all the coefficients are distinct. I mean, all the ai times y minus bi terms are distinct. So you have this beautiful case that this polynomial for every such y substitution is x to the p minus x. Why is it important? We will use this fact. For every y which is not a direction, the substitution gives you a polynomial where all the middle terms are missing, are 0. And if you see this form in the second row, that it's x to the p times h1 times y1. So if you have an hi here, for every y which is a direction which we didn't, which your set didn't determine, this polynomial will be 0. And if a degree d polynomial is 0 in more than d points, then this is everywhere 0, right? So if for some reason we can read that a coefficient of this polynomial is not 0, say the i's coefficient is not 0, that means that the number of undefined directions is less than I. So let me repeat. If for some reason we can read from the polynomial that a certain coefficient hi or hj is, yeah, here it's written, yes, hi is not everywhere 0, then the number of directions is at least p plus 1 minus I. Clear? So this is the algebraic, this is the important point. This is the way algebraically capture the property. And this works over finite fields. That's the beauty of finite fields you have. So our task now is to show that if we have many points, then the number of directions is large, and and the way to show that we will guarantee that one of the coefficients is not 0. And if one of the coefficients is not 0, then we are happy. We know that the number of directions which are defined is at least p plus 1 minus I. Again, for every y which is not in your direction, the corresponding all hi's will be 0, but the very last one, because of this one down there, the last row, you see. Okay, so this is Rédei's theorem, and the conclusion is, if you understand the structure of such polynomials, then the number of degrees is, oh, well, this is just about the polynomial. This is not the corollary. We won't actually use this theorem, but that's how he proved that the number of directions should be large. And here is the theorem that the number of directions is at least that much. And they use this beautiful polynomial method. But what can you do if there are some other nice results? Actually, one can describe the unique set which has only that many points. That's by Loas and Scriver. So, but what can we do if the number of points is much less? Because that's the real, in many applications, that's the most important thing. I will come back to Paley graphs in a minute, but let's do directions first. From there, we will be able to do to reach the bound we want to prove. So Szönyi extended it. So what if the degree, if we have n points, you still have this property that all the coefficients. So if you substitute a y, which is not a direction defined by your set, then you have this x plus something, and this something are all distinct. So you have a fully reducible polynomial. So all the roots are distinct as fx. And there is a way to construct a polynomial which will help you that whenever y is such that all the terms of the product are distinct, so as x plus something, and this something is distinct for every I, then you can extend it with another polynomial. This is this fxy, which will add you the missing roots. So the strategy is, Szönyi strategy was that construct the polynomial fxy such that whenever y was not a direction, so that means that hxy or hxy with this y, or hxy not, say if y not is not in D, divides xp minus x. So that's a polynomial, but you can actually construct this polynomial. This is still a nice polynomial. And then we still have the property of what we want about the direction, counting directions, because you see it's still x to the p minus x. So in this polynomial, we still have that if we can show that one hi is not everywhere 0, then we have many directions. Okay?
Jozsef, sorry, can you say how do you construct it? A couple of minutes.
So yes, you use symmetric polynomials. And let's just, so the definition of this polynomial as Szönyi did was recursion. So let's see just the first one. Let us suppose that you need you need that the p minus 1, the coefficient of p minus 1 is 0. Okay, so you have this set, the y's, which are not in your direction set, and you have the complement of it. So you just have to add the symmetric polynomials, well, in this case, just the ones, yes, the missing degree 1 polynomials to guarantee that the sum, so here you have this hxy times fxy, yes, and you want that p minus 1 is 0. This is the first thing, yes. So for that, you just need the symmetric polynomials, right? So you need that the sum of the coefficients is 0. And you have some coefficients from this hxy and from the complement. So if you take the minus of this one, that will give you the other one. I'm not sure I explained it in any reasonable way. It's also in our paper with Daniel and Ethan or on archive, because we repeated the argument of Szőnyi. Right. So you define first the one which will give you, I don't know. No.
I guess I get some feeling for it. You don't have to. If it's not so easy to explain, I think you can go on with the rest.
I need the formal write-up of that, and yeah. So please refer to the well, either Szönyi's original paper, because the original is the best, or our archive paper where we explain it. I know that my students suffered more with those symmetric polynomials, and I trusted them, and I saw that it's working, but it wasn't my idea. It's neat, so it's not obvious. Your question is actually very right, but luckily I just use Szönyi's result here, so I can say that here is Szönyi's result. Yeah, good.
Okay. Okay.
So let's go a little, but so far, are there any questions? Because this is a beautiful method, and I really want to advertise it, this Rédei polynomial and the application. So if there is any,
well, actually, I have another one. Yeah, sorry. Can you say again, why do we get this p plus 3 over 2? So that, why exactly is that number that I missed somehow? N plus, well, here it's n plus 3 over 2, but before it was p plus 3 over 2.
This one.
Yeah, yeah. How does it follow from these properties of a polynomial?
From this.
Yeah.
So you see that we are searching for an age I which is not identically 0. If we can show that there is a coefficient which is not identically 0, then we are safe, yes?
Yeah, yeah.
And here is the theorem of Rédei. That's what he used. But I will show you in our application, I will prove the bound what we got. But here, for this, if you ask, then here it was an application of Rédei's theorem. So the theorem is that, that this, if you have this form, x to the p plus gx is fully reducible, if it's fully reducible, then the degree of g of the second term is at least p plus 1 over 2.
Ah, okay, okay. So this is we
haven't
really
the whole
discussed
configuration.
this.
Well, I didn't tell you, but when you really apply this thing, then you start this whole game with to guarantee that infinity is a direction. So you add this one. So that's where you get the plus 1. Okay.
Okay. Okay.
But that's Rédei's. Whatever we do, that should be proved. And where were we? Here. So this extension polynomial. So the important thing, and that's what we are going to use, is that such fxy exists. And using that, we can apply whatever Szönyi did, almost the same strategy. But let's see, what can we do? So our interest will be on Cartesian products. So we will we won't really, so we need a better bound. This bound is not good enough, what Szönyi and Rédei and others did. But we can, in our application, as often it happens in additive combinatorics, this is a Cartesian product what we are working with. So we have A cross B. This is a Cartesian product. We write, so we have a set A and set B, and we have A times B, I mean the product of the n times m points, the Cartesian product. We write the same polynomial as before, and we are using Szönyi's extension. But now we will check this polynomial in a special direction, the y equals 0, which is in D. So this is a Cartesian product. This is there. But still, this is a polynomial that we can check. Okay, so we want to show that some of the, or a relatively large CI is not 0, right? In this form. Then we know that the corresponding age I is not everywhere 0, if we can prove that. And that gives you a bound on the number of directions. Right, so we have this form, and what we want to show that there is a CI which is not very large. So somewhere at the beginning, there's a CI which is not 0. And if we can do that, then by the previous observation, what we had here is that if HI is not everywhere 0, then D is at least P plus 1 minus I, okay? Now I'm doing what I told my students never to jump up and down with the slides. My students are also watching, so that's okay. They will forgive me, I hope. So anyways, here is this polynomial. Now think about it. Just see this form. So what we did, we checked this polynomial to the special case when y equals 0. When y equals 0, then suddenly all those terms with the y multiplier will vanish, and you have such products. And every bj will be, x minus bj will be in the power of m, right? It was x minus ai times y, or x plus ai times y minus bj for every I, but now they vanished, so there are m products of that. So this is one form, and this is the other form. And here I want to show again, just to repeat, that some CI is not 0. But it's almost obvious here. Just take the derivative here. In the second, do you see my pointer when I move it here, or not really?
Yeah, we do see it.
Okay, thank you. So if you take the derivative, then this term will vanish. And the first term what you will see is Ci plus 1, or Ci, which is not 0, times x to the p minus I minus 1. Yes? So if you take the derivative here, then you will see that the first term, which is not 0, will be the Ci, what we are looking for, times x to the p minus I minus 1. Agree? On the other hand, you see here, if you take the derivative, so this polynomial has roots with multiplicity m and n roots with multiplicity n. So the number of this polynomial has many roots, and of course the degree is a bound on the number of roots. So the degree is an upper bound, and the lower bound what you have, just roughly from the derivative, you know that every bj is the root of this polynomial with multiplicity at least m, right? In the derivative with multiplicity m minus 1. So m minus 1 times n is a lower bound on the degree here, which is j minus 1 or I minus 1. I don't know what letter I used. Right. So if you put that together, then here is the theorem. The theorem says that if you have a Cartesian product, then the number of directions is at least this large. Okay? So it's practically A times B. There is an error term, but it's not that bad. So if you have a Cartesian product of size n and m, then n times m is the number of directions what you will see at least. And there are cases when it's sharp, but we don't know, and that's an open problem, if you really have an n by n grid. We don't think that the bound is sharp. But here's the corollary. I promise that I will come back to the Paley clique, but it's very simple now because you have, say, a clique in a Paley graph. That means that a set A where all the differences are quadratic residues. You take A cross A, this Cartesian product, and please note that all the directions are quadratic residues because the difference of the coordinates are quadratic residues and you divide one by the other. So it's quadratic residue. So that means that the number of directions is not more than p minus 1/2 plus 2. And that's it. So you apply this, direction thing, what we went through, this polynomial bound, this polynomial method, and you get the desired bound, the same as handsome matrices. Right. And here is another beautiful Paley graph. So this bound, what we got, is far from being sharp, not only here, but in general. Again, the conjecture is that the right number should be a power of log, say log square, or I don't know what people really think about it. But that's it. So that was the upper bound on the Paley graph. And Andrei, sorry, I didn't explain you how to find this fxy, but as I said, this paper is available on arXiv, where hopefully you will find the answer to your question as well. So thank you.
Thank you, Jozsef.
Thank you. Are there any questions? I have two questions. So first of all, your bound, your last bound works for two different sets as well, right?
Yes.
So you obtain that. So can you obtain that if we have the sum set A plus B in the quadratic residuals, then the sum is direct? So can you repeat the result of Hansen and Petrov?
Yes. Yes. So in our paper, we also consider those things. And of course, you can consider other subgroups that also.
Mm-hmm.
Yeah.
Mm-hmm. Mm-hmm. Even more general subgroups.
Well, we didn't, so for those applications, we didn't do more than what they did. Actually, I think maybe they did slightly more because they considered Sarkozy conjecture and things like that. We didn't go into the details. Our task was to show that if you have Cartesian products, then you have a good bound on the number of directions. And we think that it has various applications. And this is a different angle to prove the very same result. So I really don't know. I have a feeling that there is now a new boundary which will be hard to break. But maybe a better idea will give a new result. Right.
And the second question, so it seems like that this technique works in general fields. you just obtain bounds in terms of characteristic, and that's all, right?
So it's I'm not sure. So when you have prime powers, then that there are difficulties. So Kyle is my student is now in the audience, and he worked on the Paley bound for prime powers, and was not able to use the directions argument. But of course, there are parts you can save, but not much. So we really just stayed with the prime case. But you're right, one should be able to do something there as well. Yeah.
Yes, it's important to distinguish the prime filter and the general Galois.
Yes.
Yeah. Okay, are there further questions? If not, that thanks, Joseph, for very exciting, very interesting talk. We can unmute and clap, I think.
Thank you very much.